How's it going, ladies and gentlemen? Mr. John here again, looking at 20.6. Alright, so it says based on the reaction below, which of the following would not change the measured cell potential? So one way to think of it is mathematically with the equation E equals E naught minus RT on NF ln of Q, which in this case, the ln of Q would be the Sn plus 2 concentration times the pressure of H2 all over the concentration of H+. So mathematically speaking, let's see, lowering the pH of the cathode in the compartment would change the pH, would change the H+ concentration. So that would change the E naught, because changing that number is going to change the whole thing. Addition of more tin metal to the anode compartment. Tin metal is not going to be in our expression, so it shouldn't mathematically have any effect. All right, increasing tin 2 ion concentration, that's saying changing this number, that would definitely change the value. Increasing the pressure of hydrogen gas would change this number, which would change our voltage. Any of the above will change. Nope. B wouldn't change because tin is a solid. So think about this. The concentration of the solid isn't going to change. It's a solid. It's, dropped out of every equilibrium expression that we've ever used because it's a pure substance. Its concentration isn't going to change. It's a solid. It's packed in. Whereas the concentration of things in solution, well, that can change. You can add more H+, remove it. H2, you can change the pressure, which would change the concentration of a gas. So really, tin metal, adding more metal isn't going to change the voltage. All right, number 2. The standard cell potential for the reaction below is positive 1.1 volts. The cell potential for this reaction is blank when the concentration of Cu plus 2 is this number and Zn plus 2 is that number. So again, we're going to need to use this equation. E equals E naught minus RT over NF ln of Q. And now this simplifies to, if it's at 298 Kelvin, which is like room temperature, which it is most of the time, well, then we can say T is a constant, R is a constant, F's a constant. We can simplify this to become E equals E naught minus 0.0592 volts over N, the number of electrons transferred, log of Q. And I've changed from natural log to log base 10, so don't let that trip you up. So all these problems, you can pretty much use this version of that equation because unless it says otherwise, it's going to occur at 298 Kelvin. All right, so let's do some number crunching. Well, E equals the E naught, which is that 1.0 volts, minus 0.0592 over, well, let's see how many electrons are being transferred. Cu goes from plus 2 to 0, so that's 2 electrons. Confirm. Zn goes from 0 to plus 2, that's also 2 electrons, so it's going to be over 2 times log of the concentration of the product, which in this case is the Zn plus 2, so 3.5, all over the concentration of the reactant, which is this 1.0 times 10 to the minus 5. You plug that in and you get 0.935, 0.94 volts. And if you didn't get that, it's because you plugged it in the calculator wrong. You did it wrong. Stop doing it wrong. Do it the right way. Get that answer. All right, number 3. Same kind of problem. The standard cell potential of a voltaic cell constructed using cell reaction below is 0.76 volts. If the pH2 is 1 atmosphere, the Zn plus 2 is 1 molar, the cell potential is 0.66 volts. What is the concentration of the H plus in the cathode compartment? So we're trying to figure that out. So let's work with some numbers. And by numbers, I mean letters. E equals E naught minus 0.0592 volts over the number of electrons transferred times the log of Q. Right? So why don't we rearrange this? Because we're interested in that Q expression because it's talking about concentration of one of these things. So let's rearrange that. So they get log of Q equals the E minus E naught times N all over 0.0592. And let's plug some numbers in. All right. So now to get Q by itself, it's going to have to be 10 to that expression. And this number right here, we get to be, so when we plug in the numbers, we get, I think it's 0.2 over 0.0592 as the expression for Q. And we get Q equals 2398.8, 2398.8. So that's our Q. So what is our expression for Q? It's going to be the products, Zn plus 2, concentration, times the pressure of H2, all over the concentration of H plus, squared, because of that 2 right there. Now what we're trying to find is H plus. So we do a little more algebra, and we get H plus equals the square root of Zn plus 2 concentration times the pressure of H2 all over Q. So when we plug that in, plug those numbers in, we get a Q of 0.02 as our final answer, molar for the units. Right? A little bit of crazy math there, but it's math we've done. All right, 4. Voltaic cell is constructed with 2 silver chloride electrodes, where the half reaction is given below. Now this information right here is the reduction potential. But if we think about it, we have this going on. So we have Ag being oxidized and reduced. So we're really getting, all right, reduction potential of 0.222, and also the oxidation potential of that being negated, so minus 0.2220. Which equals 0 volts. That's our E naught. So our E naught is 0. So when we have this equation, RT on NF ln of Q, well, E naught is 0, right? So what we're really saying is that E equals that 0.0592 all over N log of Q. Now, I just made a switch here, right? I switched from the natural log to log base 10, and I almost forgot that negative sign there. So now I look at, well, how many electrons are being transferred? It's just 1. Silver's going from +1 to 0. So that N is 1. And my log of Q, all right, well, let's think about this. What's going to happen? If I have 2 half cells, right, hooked up, got the load to my other electrode, and they're both filled with the same stuff, all right, well, let's say that this one's more concentrated. That means I have more cations of silver there, and then this one is more dilute, which means we have fewer cations. What we want to do is we want to increase the Ag plus over here, and we want to decrease the Ag plus on this side. So this side, the concentrated side, is going to be the thing that gets reduced. So we're going to start over here is going to be where it's Ag plus becoming Ag0. So that is going to be our cathode, right? So our cathode is our concentrated side, and the dilute side is going to be our anode, is the dilute side. So we're going to start with Ag plus 0. Ag plus becoming Ag0 in our cathode, and Ag0 becoming Ag plus in our anode. So the concentration Q is going to equal the dilute, concentration of the dilute, all over the concentration of the more concentrated one. So that is what our log is. So what are we solving for? We're solving for E. All right, the dilute is the 0.0222 and the concentrated is the 2.22. So that's the concentrated one. So we just plug it in and we get a number, and we get 0.118 volts as our number when we plug those things in and solve. That's it. A few more. 5. The standard cell potential for the reaction below is positive 0.63 volts. What is the cell potential for this reaction when Zn plus 2 equals 3.5 moles and Pb equals 2 times 10 to the minus 4? All right, so again, it's the same equation we've been using. E equals E naught minus 0.0592 all over N times log base 10 of Q. So Q is going to be the products. So the concentration is Zn plus 2 all over the reactants, which would be the concentration of Pb plus 2. So we just plug that in, right? So Zn plus 2 all over Pb plus 2. Let's plug some of those numbers in. 0.63 volts minus 0.0592 all over how many electrons are being transferred. Pb goes from positive 2 to 0. That's 2 electrons. Let's look at zinc to confirm. It's going from 0 to plus 2. It is also 2 electrons. So it's over 2 times log of Zn, which is 3.5, all over the Pb, which is 0.00020. And what do we get? When we plug that into a calculator, we get 0.50 volts. That's our answer. Yep, well, 0.504, which would be 0.50 sig figs. All right. And number 6, the last one for the section, the standard EMF for the cell using the overall cell reaction is 0.48 volts. What is the EMF generated by the cell when we're using those concentrations? So E equals the E naught, which is 0.48 volts, minus 0.0592 all over N, which is, let's see, Ni goes from plus 2 to 0. So that's a 2 electron transfer, confirmed by looking at zinc, goes from 0 to plus 2. So it's definitely 2 electrons, log of Q, which would be the product. All right, well, my product is Zn plus 2, so 0.100 molar all over my reactant, which is that Ni plus 2, which is 2.50 molar. And I plug those into my calculator and I get 0.52 volts. And that's it. That's all I got for this section. All right, bring questions. See you in class.